Hi, everyone. My name is Daisy Hollman from Google. I am talking about cute C++ tricks. Basically things you shouldn't do in code, but will hopefully maybe stick in your mind and help you learn something that maybe you can use in code. So, I mean, the goal here is to mostly to geek out and have fun. I'll be honest, I really enjoyed writing this talk. I did something like it last year. I really enjoyed doing it this year. But it's also about learning about how C++ works in the dark corners that you may come across in real code, and then understanding what's going on there. And I think that's actually really important. And if you use these things in such a bizarre way, then hopefully the reasoning will stick in your mind a little bit. You'll say, oh yeah, like I came across this compiler error in my real code. Like now I understand why that's coming up because, you know, I saw this cute snippet that did something really bizarre and like, you know, used, I don't know, lambdas to make a tuple that printed hello world backwards or something. In general, hopefully we can learn a little bit about the right way to do the same thing. But I especially want to teach people how to learn C++, so how to play with the language in a way that will help you gain more insight into what's going on. So this talk was, part one of it was given at CppCon 2021, and then at Meeting C++ meetup of some sort right before Meeting C++, and then I talked about it on CppCast, and I was really flattered and really enjoyed the fact that people liked the talk because I really liked making it and wanted to make more, and so here we are with part two of it. Some of these tricks have been presented at other C++ conferences earlier this year. There are new ones in this talk. There's one in here that I haven't even put on Twitter yet because I'm afraid of the number of implications that I can't talk about compactly enough on Twitter, the number of gotchas. So I'm looking forward to hopefully talking about that. But first, I want to throw in a cute inclusivity trick of the day. I've gotten a lot of positive feedback on my cute tricks talks. One person came up to me at work actually and was like, hey, I saw your crazy C++ tricks thing. It was fascinating. And I wanted to just take a second to say, like, when you say these things, think about the implications of the words you use for the people who have been called those things before, have been referred to those words. And particularly if a word has a negative connotation that stigmatizes an entire group of people, maybe try and come up with a better word that means the same thing. Yeah, I know not like everyone is bothered by this, but there are people who are, and we have plenty of other words. English is a huge language, so we have plenty of other words that mean the same thing. I suggest outrageous, egregious, preposterous, cute. But there's a reason I don't call it my crazy C++ tricks talk. So maybe just some food for thought that I throw in here, since I have a captive audience. Okay, disclaimers about this talk. Don't use these directly in real code. Some of them did come from real code, which is kind of scary. But do use the things that you learn from them, the concepts to help you understand existing code, and maybe understand how to do something in new code that will be readable to the people that you're writing it to. This is definitely not a software engineering talk. I recommend Titus's talk for that. So well-written code, good software engineered code should be unsurprising. That's like one of the most fundamental things about it. And this talk is intentionally about things that are surprising and so catch people's attention on Twitter in 25 lines, and they're like, wow, I can't believe it does that. Why does it do that? Why does it work that way? C++ is so messed up. And then, you know, the whole Twitter engine gets going and people are like, wow, C++ is so messed up. And, you know, I have a problem with my talks getting too into the weeds, so disclaimer. And I've tried to fight it, and now I'm just giving talks that are all weeds. So hopefully you can follow it. I'm going to try and take it slow. This talk is also it's several mini talks. It's kind of a choose your own adventure talk, so I'm gonna try and get audience feedback at a few points and see, hey, should we go down this rabbit hole? Are you interested in this? Or should we move on to a different section of the talk? I have about 3 hours of slides in here. I will not get to all of them. So if you don't vote for the part that you want to see, you may not get to see it. So if you see, parts of this talk that you want to see, I'll ask like a either or, we'll vote, whatever. Anyway, so here we go. And right off the bat, I'm going to skip the first 2 sections because there was something in Jason's talk right before mine that prompted me to think there might be some interest in this trick. So you can't use static assert in a Constexpr function that's for an expression that's dependent on the function parameters. But because Constexpr really means like maybe this might be evaluated in a constant expression. I'm gonna get into what that means a little bit later. But you can just use assert, right? You can also throw, as we saw in the last talk, unless you're like at a company that compiles with no exceptions, which I don't know any companies that do that, but you can do things as long as it doesn't evaluate false and do things that you can't do, right, in a Constexpr function. So we're gonna walk through why and how that works. This is like a simple, very simplified A to I function that goes through and accumulates the value for positive integers. It skips digit separators, which if you didn't know about C++ digit separators, now you know about C++ digit separators. So it's a single quote. And it asserts that, we have valid characters in here, right? And this works at Constexpr time. This works at compile time. So what does Constexpr mean? Well, meme, wow. That was a fantastic slip because there is an appropriate meme for this. So it's like the name 3 something meme and name 3 keywords. Well, Constexpr is at least 3 keywords. It depends on which Constexpr you mean, right? So Constexpr variables, we have Constexpr functions, we have Constexpr if statements. There's more to this. I probably will come back to this part because I have other things I want to talk about, but let's talk about how these differ from each other, right? So Constexpr, they differ in like what part of the expression or statement they require to be Constexpr, right? I guess they're all statements, but so Constexpr variables require constant initializers, right? So the thing on the right-hand side has to be a compile time evaluated expression, right? Constexpr if statements basically says that this thing inside, or if Constexpr, if you'd rather that, this thing inside the parentheses, right, is required to be evaluated as a constant expression, right? So what's the comment with arrows for a Constexpr function? Well, it turns out it's not that simple. That would have made a lot of sense, but it doesn't meet all of the use cases. So let's look at where we can use a Constexpr function, and maybe that will give you some idea of how it works. So if a function is declared Constexpr, right, our Constexpr function from earlier, then we can use it on the right-hand side of a Constexpr variable initialization, right? We can use it inside of a static assert. We can use it in a non-type template parameter, right? But only as long as its arguments are also constant expression, right? So Constexpr kind of means like, you can do this at compile time. If the things you pass to me, you can do at compile time, right? It's kind of like a recursive thing, like a recursive if, I don't know how to say that. Anyway, obviously this program doesn't work, right? You can't take runtime input and validate it at compile time. But you can do this, right? You can call a Constexpr function at runtime with runtime input and have it work. And this is really consistent with how C++ does a lot of things, right? C++ has templates that you write once and work different ways for different inputs, right? And Constexpr is kind of the same way. It's like, well, you write it once and it works as a compile time function or as a runtime function, right? And that's why C++ does that. It's just that the fact that we reuse the keyword in all three different places, when one of the places it means like, maybe this could work this way. And the other two, it means like, definitely it has to work this way. It's maybe we should have used up one more keyword in order to do that or something, like const maybe or something. I don't know. Someone wants to write a C++ 26 paper, ping me on Twitter. So what does maybe Constexpr mean? So a Constexpr function that never can be used in a constant expression is ill-formed, right? So this actually gives a compile error if you try and do this. If you declare a namespace scope variable and then try and increment it inside of a Constexpr function, you get an error. Awesome. But it's the worst kind of ill-formed. It's ill-formed, no diagnostic required, which if you ever see that in something that you're doing, run. No diagnostic required is the area of C++ you don't want to touch, right? And so this actually compiles fine with Clang, right? This function is totally okay, right? Because as long as you're calling it with false at compile time, all of your compile time invocations are false, then the throw zero never happens, right? But this function is ill-formed, no diagnostic required. Because it would require the compiler to solve a hard problem, right? It would require the compiler to dig deep down and find out that it is calling a version of a different function that has non-Constexpr behavior in it, right? And templates are the same way with respect to their template parameters, right? So if this actually is ifndr, but it compiles fine with Clang. GCC is able to diagnose both of these last time I checked, which is impressive, but not required. I think GCC diagnoses this one, but not this one, actually. Either way, the point is that it's the same with respect to the parameters and with respect to template parameters, right? Because this could be instantiated with a different template parameter that would, in theory, cause the body to work differently. And I mean, in practice, obviously, the body could never work differently with a different template parameter. Humans can see that, but that's something that's very hard for a computer to see, right? In general. So why is this ifndr? I've already said this. We don't want to really force compilers to solve hard problems. Compiling C++ is already a hard enough problem. So yeah. In a nutshell, this is what ifndr means. The compiler is allowed to say this is fine when the room is burning around you. So why are we allowed to do assert inside of a Constexpr function? Well, remember this I showed earlier, right, is basically, this is actually an example pulled directly from the standard, right? And these all work fine as long as we call foo false in all of these contexts, right? It's fine. The assert macro is usually defined something like this. This isn't pulled specifically from any specific library for license reasons, but it's actually, it may be pulled from Muscle, actually, because that one had the most permissive license I could find. But anyway, basically, you get the idea, right? It's the same thing as this function up here, right? It's a ternary expression. And so if assert expression is only a constant expression if expr evaluates to true, right? And so until recently, actually, the error you would get if you had an assertion fail in a Constexpr function and tried to force it to be evaluated at compile time was that the surrounding function is not a constant expression, which is not very helpful. I pointed this out, and at least the Clang implementers, I believe, have fixed this now, which is amazing. I love that our community is such that you can say like, hey, this isn't the most helpful diagnostic, and then like a few weeks later you have something there. But yeah, so that's exactly what we want, right? We want the code to not compile if the assertion fails. That's the point of assert, right? So it can't be a static assert, right? Because of the way that parameters work and because of the way Constexpr only means maybe constant expression, right? So if you give it a runtime parameter, right, and then you were to use it in a static assert, obviously you can't evaluate that static assert at compile time, right? Just going back to our example up here, right? If this here were instead, this static assert were instead inside of a function that's marked Constexpr, right? We'd be allowed to call that function because you can call Constexpr functions at runtime with runtime information. But then obviously you couldn't take this value and use it in a static assert, right? So that answers the question from Jason's talk, maybe trying to go a little deeper on it. Not that Jason didn't do a great job of answering that. He said essentially the same thing, but. So what does Constexpr really mean? I think Barry's paper P2448, which may change some of this, says it best that, time check, okay. The Constexpr functions and function templates in general mean maybe Constexpr. Not all instantiations or evaluations must be invocable at compile time. It's just that there must be at least one set of function arguments in at least one instantiation that works, right? So you can't write something that can never be instantiated as Constexpr. And then his paper follows up with, but who cares, right? Why are we forcing IFNDR into the language when it doesn't hurt anything? And this is actually a good read if you're interested in this problem. And I don't know if it made 23. Someone can update me after the talk if so. But I hope the change gets in because it's really, it's unnecessarily introducing ill-formed no diagnostic required to things that don't really need to touch those demons. So yeah. Any questions about that section before we jump to the one that I want to talk about and have been promising several people I'd talk about this morning? No? No questions? Okay.
One comment.
Yeah?
That paper is probably going to make C++ 23.
Okay. Timur says the paper is going to make C++ 23. So yay!
Well, the committee has to actually vote for it.
It's probably going to make C++ 23.
It's on the schedule.
It is scheduled. That is fantastic news. That means that simplifies a little bit. So it basically means that Constexpr means all those same things, except that if you do it wrong, it's not IFNDR. It's just well-formed but meaningless. Which I think well-formed but meaningless is actually something we probably should have more in C++. Anyway, that's another discussion. So this one is one of my favorites to talk about. I talked about it a little bit at C++ Now in a slightly different context. So counting aggregate members. So if you, here's the trick, and I'm going to break it down very extensively. Don't worry, this is the longest cute tricks section I've ever written. And we will have some points at which I'll ask the audience if you want to skip or not. Basically, what we want to get to, though, is this thing at the bottom, right? We want to be able to statically say, hey, foo is a type with that's an aggregate of 2 members, and the number of aggregate members is 2. So what's going on here? Let me read the way I phrased it in the tweet. C++ doesn't have much reflection, but you can figure out how many members are in an aggregate by trying to construct it with objects that are convertible to anything. So we're going to break that down one at a time. This trick, I don't know if I'm ashamed or proud to admit that this trick is actually in the Google code base. I think I'm allowed to say that much. And a significant amount of code depends on it. And it currently has a bug, which I will file a report for in this talk. So yay, but it's also caught some bugs, so anyway. So objects that are convertible to anything. Well, what does that mean? So we have these things. If you're not familiar with trolling style C++, I'm just kidding, but we have conversion operators, right? So you often see this as operator bool or something like that, right? That's the most common use of this. But our conversion operators, you can actually template them, right? And so this is literally like, says this is convertible to anything, right? That's how you word that in C++, which is kind of bizarre to think about it. The first time you see it, it kind of blows your mind. But this is like an unconstrained template conversion operator, right? So it's saying anything that you try and convert this object to should use this function to do so. Which means that if you ask if it's convertible to something, you're going to get back true. Right? So we can then try and construct it. And so in C++20, we have a much nicer way of saying that. We say requires. And we say requires construct something with instances of any. We need a way to repeat something n times, right? Given a number n, we need a way to repeat something n times, and there's no like built-in language way to do that. And part of the reason why there's no built-in language way to do that is it's actually relatively easy to do with some things that are already in the language. I think that we still probably should eventually have one. But so here's one way to repeat something n times. I go into way more depth on this in my talk at CppCon last year, if you're interested. But basically, in C++20, we can give explicit template parameters to a lambda, right? And then deduce that template parameter as part of the call to the function, right? Just like we can in a normal function. And so using that, now we have a parameter pack that is this many, that is n elements long, right? We can also do that in a requires clause, and we still have a name for the parameter pack inside the requires clause. We have to do a requires on the lambda, but it does allow us to have something named, have a name for something that is in things long, right? And then we can use this really cheesy alias template that's, I call repeated with, right? And it just gives back the type, but it takes a second template parameter that it doesn't use, right? And so if you were to stick that sequence in there, you would get this repeated once for each element of this parameter pack. Did everyone follow that? Does anyone have any questions there? I see some shaking heads. Should I go through it again, maybe a little slower, or? Yes. Okay. So here we have a lambda, right? Remember, lambdas work just like regular function templates when they're generic like this, right? And std index sequence is this type trait helper utility in the standard library that just has a sequence of integers as its template parameters, right? They're non-type template parameters, they're all integers. It's actually an alias template for std integer sequence, but we're just gonna gloss over that for a second. And std make index sequence is a helper that makes an index sequence of length n, right? It actually, at this point, in every implementation I know, uses a compiler intrinsic to do this, so it's actually relatively fast at compile time. And so it makes the sequence, 0, 1, 2, ... n minus 1, right? So this parameter pack, which we are deducing in the lambda, right? We're deducing it as the name this, the name IDX, right? We're deducing that name, right? It's like a pattern matching type thing. This is how templates in C++ generally work, right? We're deducing that pack to be a compact name for 0, 1, 2, 3, ... n minus 1, right? And so that when we expand that pack, right, we will get one expansion of the expression for each element of that pack, right? So we have, when we expand the pack here, right, this ... refers to everything before it, right? And so this means that this repeated with alias template will be, it'll do a repeated with 0, repeated with 1, repeated with 2, repeated with 3, ... repeated with n-1, right? And here we've defined repeated with to just give us back any directly, right? So this is just going to be any n times. It just throws away the index because it doesn't use it on the right-hand side, right? But that helps us expand out this pack. So we've taken something that we have a name for now, and we've stamped out n copies of it, right? And so now you can see, given a number n, we have tried to construct it, right? We've tried to construct some type with n copies of this anything, right? And that is essentially the statement we made up here, trying to construct it, right? We've had to do some mess with having to write requires 3 times, and that's because you can't partially specialize a concept, but you can, partially specialize or deduce a template parameter, not partially specialize, but deduce a template parameter of a lambda used in that context. And so because this requires clause requires the evaluation of this lambda to be a valid expression. So we've required the evaluation of a lambda to be a valid expression, and that lambda is constrained on a requires clause, right? So it's effectively like putting this requires clause into this requires clause. That's another kind of mini trick in here. Did people follow that? Yes, I got some thumbs ups. All right, must be doing something right. And if you're not following it, none of this is simple. None of this is simple. Like they asked me to check like the target audience, beginner, intermediate, advanced, expert. I always check advanced expert for these talks. And like, that's mostly because if I didn't check advanced, they wouldn't give me the time slot. But I do think that there's something everyone can learn here, even if you don't follow every single step here. I want to have something here in this talk that appeals to people who have been involved in the committee for 10 years and who are coming to their first conference also. And I think there's things to learn in there. Mood check. Should we go deeper on this? This is the any expression. Turns out doesn't work. I'm getting a thumbs up from Andy because it is a bug that he currently has filed. I'm getting thumbs up from Z. Okay, let's talk about this, because I learned this morning. This is the first time I've ever asked Richard Smith something and gotten a, wait, what? back. So I'm trying to distill the answer that we figured out during this morning's break into some slides. We'll see if I succeeded or not. So yeah, so we have this constructible with, right? We have this repeated with. It works. Works like we'd hope. Wow, I copied this slide. Wrong. Oh, okay, yeah. No, it's the same thing here, right? But so it works with like things that have constructors. It works with aggregates is the important point I was trying to make on this slide, right? Because aggregates implicitly have constructors that take subsets of their members, right? If we declare constructors, if we declare multiple constructors, it works fine, right? This is just showing that what we did previously. But what happens if we try to construct, that is, okay, that works fine. Oh, I'm sorry. Yeah. Why is this a valid program? Can anyone tell me? Yes, copy constructor, move constructor, right? So any deduces foo. The any operator conversion template deduces foo and finds the implicit copy constructor, and it works, right? So we need some way to exclude the copy and move constructors. We also have this case where foo takes an int ref. And this doesn't compile either with our current version of any. We need some way to make any convertible to an L value reference.
So my question was about the second code snippet here with the question marks. Is this going to work or break with the, because there's a copy constructor which takes one argument as well as a move constructor which takes one argument.
Yeah, and so the answer is essentially that C++ disambiguates between copy and move constructors all the time, and so those are actually well ordered. I will show you some cases in just a second that are not well ordered and cause all kinds of mess. So we need to make any convertible to an L value reference somehow. So we can just do this, right? This might look like the greatest apparition you've ever seen. Although it can get worse. You can actually R value qualify this thing, and then you're just making memes in code. But yes, this is saying my type, not only is it convertible to anything, it's also convertible to an L value reference to anything. So if you put it on the left-hand side of an assignment in any implicit conversion context, go ahead and be okay with that. It is not a very meaningful statement in real code, but it's something C++ allows us to do and turns out to help us out here. So now, if we do is convertible any to int ref, we get this working, right? But now we've broken our original thing. Now it's not convertible to int. And I had something in this slide for why, and then I asked Richard about it, and he was like, no, that's not actually why. I did have this part right, conversion to int is ambiguous. But the reason is that it's because whether we are taking a value, or in this case an R value, or an L value, these are both perfectly acceptable constructors, right? You get two different options that are equally valid. And because the standard says that multiple conversion operators are unordered, right? Absent any other rules, which I'll get to some of these other rules in a minute, but if you have multiple conversion operators, they are unordered with respect to overload resolution, which means that this is ambiguous, which means that it's not constructible, right? Substitution failure is not an error in this context, right? And so it just says not is convertible, which is frustrating. So what if we do this? What if we make this an L value reference and an R value reference? And when I got to this point, when I previously did this way back in 2016, I was like, well, it feels like this should work differently. I had no idea why it works differently. It just happens to work. Now it's convertible to int. Why in the world is that? Well, there's a specific clause in over.ics.rank, paragraph 3.2.3, that says if all of the overload operators include reference bindings, then there is an ordering in which you prefer the L value reference over the R value reference. And that was done for backwards compatibility reasons. But we can keep going. What about move-only types? I actually got a tweet response to my tweet that said, like, bug report, this doesn't work for unique pointer. Which I hope it's not a bug report because I hope they're not actually doing this in real code. I don't know anyone who would do this in real code. I definitely have done this in real code. If we have this form that we're talking about here, and we have a move-only type, it, in all three major compiler front-end implementations, all four major front-end compiler implementations, this says it's not convertible. So it's not just like some bug in the compiler. There are tons of bugs in compilers around this space, by the way. Particularly in GCC 4.8, 4.9, I feel like the behavior of this changed every sub-iteration, 4.8.3 to 4.8.4 to 4.9.1. So if you live in that world, you still live in this pre-GCC 5 world because you're in embedded or whatever, don't do this. You're asking for hell. Is there a question back there? No? Okay, I'm sorry. So yeah, this doesn't work. It went from working to not working to working to not working several times. We are fairly sure that we know that what the standard says is that this shouldn't work at this point. So when the compiler builds a list of candidates, it considers deleted constructors as part of the candidate set, and then it only errors or substitution fails, depending on the context, if the candidate is selected, right? So that's really key here, is the order in which things happen, right? So the point of a deleted copy constructor, right, is that you want to get an error if you try and copy the thing, right? But before then, right, when you're building the list of candidates, you want to include it in the list of candidates so that you do get that error, right? Otherwise, you would get like no function found, right? You actually want to get a, hey, this is deleted, you can't do this, right? And so it gets included in the list of candidates, right? So there is a copy constructor that selects this operator. I think I explained it in this next bullet point, right? There's a copy constructor that selects this operator, and there's a move constructor that selects this operator, right? And those are ambiguous. And before it even finds out that it's deleted, it finds out that it can't select an operator. And so it decides that that's a substitution failure at that point, before it's even tried to instantiate the copy constructor. I think instantiate's not the right word there. Somebody's gonna correct me online. Barry, you can comment below. Yeah, before it's even selected, right, the copy or move constructor, it decides that it's ambiguous. And so something that's ambiguous is a substitution failure, and therefore is convertible fails. We can, this is worse. It gets worse. What if I do this? What if I have a weird move-only class that has a requires false clause on its copy constructor? Yeah, so Timur says that's fine. I would hope that no one else in this room is twisted enough to have thought that that should be the default behavior. It makes sense once it was explained to me, but this actually is, any is convertible to this. And that's because of the order in which things happen, right? So because requires false is here, right, it doesn't get included in the candidate list, and therefore it's not ambiguous, right? And so this is kind of how we figured out how this was working. Go ahead, Titus.
There we go. Did you just effectively say that requires false is a different way to spell equals delete that is better or worse in some weird cases? Is that what I just picked up?
I didn't, it is a different way to spell equals delete that works differently with Sphene.
This language is so weird.
You should never, I never recommend doing this, to be clear. But, right, it trips up a different part of Sphene, right? It trips up the creation of the overload list rather than the instantiation of the overload list, right? And so if you want your Sphene to work that way for some reason, which I'm sure Eric Niebler has a reason for this, I'll be honest, probably people who have written things like ranges have reasons for this. You can do that. We can keep going. So if we do this, which is what I figured out in 2016, by random guessing, it works. And I had no idea why this worked. Until now, hopefully, after explaining this, you get some idea, right? Now, this const adds an extra step to the conversion sequence, causing the sequences to be qualitatively different. And with one sequence being longer than the other, there's no longer ambiguous. We could have used volatile here if we really wanted to be careful not to run into something, which is actually in cases where, I've talked to Eric Niebler about this before, by the way, in cases where you end up with needing to disambiguate 2 layers of things, you can use const and then const volatile. And it will have to add 2 things instead of adding 1 thing, and so now you have a ranking of 3 things. I believe that is correct. Somebody can correct me. But you can certainly use volatile here as the thing that's least likely to collide with real code, because people do use const, but not volatile. So this is a thing this is a known trick in that community that is used in real code. And so this disambiguates, and now we have is convertible that works. Unfortunately, if we have an immovable object, there's nothing we can do, right? Because we still have to have an expression on the right-hand side that is a function, right? And you can't do that with immovable objects. And there's no way to make that one work. We need real reflection. We need to stop having to do this. Yes, 15 minutes remaining. Confused? Me too. This was me 5 years and 10 months ago. So I've been in this business for a long time, and I just finally completely understood how this works this morning. So don't feel discouraged. And shout out to Barry Revzin for answering this like several years before I ever met him in person. He's answered several of my questions on this. He's also the author of the Constexpr paper we looked at earlier. There's a lot of great stuff for the standard, so if you see him around a conference, say hi, say thanks, because yeah, he's keeping us all sane. But wait, there's more. Okay, so this one's a little easier, right? We need to exclude copy and move constructors. And we know how to do this, right? So right, we want empty. We want empty to be not constructible with one thing, right? Otherwise, we can't detect 0, right? So let's just make a constrained conversion operator, right? So we can say, let's make a concept that says you're not allowed to deduce something very specific. You're not allowed to deduce anything. The remove CVRef is being a little pedantic here, but the point is that you're not allowed to deduce T to be the same as you, right? Compiler, you're not allowed to do that. And so now we can make an any except, right, that says your conversion operator is allowed to deduce anything except for the template parameter that I gave to this class. And we can use that and say that the first parameter, right? Notice I'm doing an n-1 here. The first parameter is not allowed to be the same as the type that we are trying to. So this is just a small modification of what we did earlier, right? Except for we're saying don't deduce the copy and move constructor. So this is like how you say the thing that we said in words in code, right? And concepts have made this way easier, right? Having to do this with Svine is a mess. And so now, that should be, yes. Oh, there's a not there. Yeah, side note, I really like the not. I know Microsoft's compiler didn't compile it well in like the 90s, and that's why no one uses it, but it's a lot more readable than an exclamation point to someone who has dyslexia and runs things together. So think about that if you have control over that in your code base. End of the going deeper section. So you would have gotten to skip over all of that if you hadn't given me thumbs up. But you wouldn't have laughed as much. So putting it all together, yeah, so now we just basically have to say an aggregate of n, right? Because an aggregate is constructible with like the first few, if the last few are default constructible, right? You get default constructors for the last n minus k members, and the constructors for the first k are I don't know, default initialized, not, sorry, brace initialized or direct initialized, one of those two. Somebody can correct me. It's one of those initializations that is different in key ways from the other ones. Yeah, so if we have a structure like this, foo, it's constructible with 0, it's constructible with 1, it's constructible with 2, it's constructible with 3, it is not constructible with 4, right? So to get our aggregate of n concept, we need to say constructible with n and not with n plus 1, right? What can we use this for? Well, I've been leading up to something really cool that you can use this for, and oh my, I have 10 minutes to do the coolest part of my talk. Okay, we can reflect on an aggregate, right? So we can take, we can create a function template, right? That takes an aggregate of 4. We can destructure it and call a callback with the data members. Now, if you've ever tried to do any kind of metaprogramming in C++ that does something like this, like try to build a JSON parser or something like that, or JSON reconstructor, your mind is absolutely blown right now. When I first saw this, my mind was absolutely blown. I'm like, wow, we actually kind of sort of have reflection if you only use aggregates. Like, but that's insane, right? You can do a lot of things with this, right? If you constrain your program to only use aggregates for things that you care about, you know, pulling out of JSON or putting to JSON, you can write something that puts all of your types to JSON automatically, right? Maybe given a name for it. You still need the name, but like you can get most of the types here, right? That's pretty amazing to me. And then you have to create an overload set, right? One note here is that because structured bindings always appear in a statement and not in an expression, you can't spine here. So you actually do have to list out all of the numbers, right? You can't just like say, if n works, then don't try n plus 1 or something like that. You actually do have to list out all the numbers explicitly and do all the destructuring explicitly. And that's because statements don't work with spine for very good reasons that I'm not going to get into here. It gets worse. So then I saw this. Somebody responded to my tweet with, you can push this further. And the scariest C++ code I've ever read. And I will try to explain to you why it was the scariest code I've ever read. Because I actually knew about this technique from back in 2014 or 2015. I knew that the C++ committee had said, so this came out in a 2015 blog post that was very, very popular. Has anyone in this room seen this post before and read it? This series of, not on Reddit, sorry, and read this post? There's a series of blog posts that was very, very popular with about 10 people, and we were all like freaking out, and then the rest of the world never saw it. But the 10 of us were like, holy cow, C++ is profoundly broken. It's worth reading. It's actually, if you're really into metaprogramming, it's worth reading. Otherwise, ask someone who is. It got a response from WG21. Richard Smith opened a ticket or an issue with Core Working Group, Stateful Metaprogramming via friend injection. And the Core Working Group decided that such techniques should be ill-formed, although the mechanism for prohibiting them is yet undetermined. This is 2015. Think about what C++ you were writing in 2015. So let me go through what it's doing really quickly. I have just enough time to race through this a little bit. It's not going to be accessible to the intermediate or advanced if I'm going to go this fast, but I think many of the experts in the room will follow this and see why this is the scariest thing I've ever seen. So you have a flag type, right? A template that declares a friend function, declares but does not define, and that's really key, a friend function named getMemberType. We declare another class template, setMemberType, that defines the friend declared in getMemberType. Now, the way that C++ talks about friends is that it says the friend has to be declared in a class that, I'm not gonna get this exactly right, but it has to be declared in a class that pertains to one of the template parameters, right? So because it's declared here, we're not breaking that rule. I thought that it also had to be defined there. It does not. So you can define it down here, and C++ will still find the definition, which is absolutely bonkers and broken. And so we can define it to return some unrelated type u. So we've effectively made this compile time map between t, I, and u, right? If we just do decal type on getMemberType, we can get back the u that was completely unrelated to t and I when we declared it. That is, yeah. It's also, we've created an excellent recipe for violating ODR, right? Like, this struct is never something you should write, right? Because we're defining something that if we ever define this as anything other than one exact thing in the entire program, then we violated ODR, right? I believe this is IFNDR. Someone can correct me if it's like IFDR and compilers are just bad at it. Now the gross part. So remember our any from earlier? We can just do this. Requires setMemberType. So that's gonna cause our setMemberType over here. I know it's small, but I'm trying to keep it all on the same screen. We can cause that to be instantiated, which causes getMemberType to be defined, which means that if we decal type later on it, we've made a stateful metaprogram, right? And we've effectively created this compile time map. And now, constructible within injects a definition while it's checking the concept. And we can get it back using this member template inth member that does constructible within. And so if I have foo, ijk, I can get back the type. This is profoundly broken, right? You can do this with functions and function parameters. You can do this with constructors. You can do it with aggregates. And this is WG21's response. It is still open issue. This is still an open issue in 2022. That's why my mind was blown when I came to Richard with this. I was like, I thought this was a core working group issue in 2015, and the committee decided to get rid of this. And he was like, yeah, that's exactly what happened. We haven't done it yet.
Can you explain, go back to the set slide, where you set the flag?
Oh, yeah.
Because it seemed like you said it had to use the type of the class it was declared in. I didn't see how it was.
Yeah.
So you said we need in getMemberType.
So getMemberType has in its argument list flag of t, I.
Right. So why is getMemberType in the setMemberType?
Well, it's declared here. It's defined here.
But so doesn't that have to use setMemberType or something? Or does it not?
For a so that was my original solution to this. I'm not sure it actually works without breaking existing code. My original solution was to say just it has to be defined. But that, first of all, precludes out-of-body definitions of friends, which is actually something that's necessary because you may need to be friends with two different templates, and you don't want two definitions for that. I still think you shouldn't be able to define a friend of something else in a class that is not a related type. And I think that probably would fix this, but I don't know what it would break. That's the question, right? We don't know what it would break in existing code. Hopefully nothing. But that's work that has to be done, right? And no one's particularly eager to do this because you can also just say, don't do this. And I'm saying it now, don't do this. But also don't do this because your code will, like, WG21 may just decide to break your code at some point. So, but yeah, it's the definition and not, sorry, the declaration and not definition. So this does follow the rule technically, right? It's just that this is, anyway. I am done, I am out of time. Feel free to find me at breaks and chat and geek out, share your cute tricks, share something you wanted to hear more about. Thank you so much.